Yeah, so thank you. So this work has been done with my PhD advisors, Omar Fauzi and Anthony Leverrier. And so we've studied the quantum expander codes in the context of fault tolerance. So in this talk, I will first show you what is the context of this work. Then I will explain you what are the quantum expander codes, and then I will show you what is our contribution. So first, the context of this work is fault tolerance quantum computation. So it starts with the following fact. Quantum information is fragile because in an experimental point of view, we are not able to store or to process the information without noise. So the natural question that comes is whether it is possible to build a quantum computer. So the answer is yes, and it has been proved in 1997 that if you're able to construct noisy gates whose noise is below some threshold, then you can simulate any quantum circuit using a fault-tolerant circuit. And so the idea of this theorem is to use quantum error-correcting codes with one logical qubit and to concatenate this code with itself multiple times. However, the drawback of this technique is that you get a polylogarithmic overhead in space and time, meaning that the number of physical qubits is this when you want to implement m logical qubits. So in 2013, Gottesman improved this result, and he proved that it is possible to do fault-tolerant quantum computation with constant overhead, meaning that if we have m logical qubits, then we can do a fault-tolerant circuit with eta m physical qubits for some constant eta. And the idea here is not to use concatenated code, but to use codes with much more logical qubits. And the point is that this theorem depends on a conjecture. And the conjecture is that there exists a family of quantum error-correcting codes with a constant rate which have a low-density parity check representation, and with an efficient decoder, and also which are robust against noisy syndrome. So in this work, what we have proved is that we have proved this conjecture. Okay, so more precisely, the main theorem that we've proved is that if you decode a quantum expander code using a decoder called the small set flip decoder, which have been proposed in 2015, then you can correct linear size errors with a high probability, even when the syndrome measurement is noisy. Okay, so let me explain you what are the quantum expander codes. So if we look at the family of codes which are available, of LDPC codes which are available, you can see in this table that the expander codes are very promising. So their dimension grows like a linear function of the block length, and the minimal distance grows like square root of n. And also, there is an efficient decoder to correct them. So if you compare with the other error-correcting codes, for example, the well-known toric code, you see that the dimension of the toric code is a constant, whereas for the expander code, we get a linear dimension. And also, something I would like to emphasize is that for LDPC codes, we are not able to construct code with a linear minimal distance. And the best minimal distance is this one. And so you can see that it's a bit better than square root of n, but it's roughly square root of n. Okay, so this slide is a quick survey on quantum expander codes. So to do that, I will use the communication scenario. So as in the classical case, in the communication scenario, Alice wants to transmit some information to Bob. So what she does is that she takes a quantum state in the code Q, and she sends it through a noisy channel. Then Bob receives psi, on which has been applied some Pauli error E. And then Bob wants to correct this error. So first he measures n minus k Pauli operators that we call the generators of the code. This gives him n minus k bits, which is called the syndrome. And then using this syndrome, Bob guesses a correction for the error that I will denote by E hat. First, in 2014, Tillich and Zemmour introduced the hypergraph product codes. So these codes are LDPC. They have a constant rate, but they did not, there was no efficient decoder for these codes. Then, in 2015, they showed that a subfamily of hypergraph product codes that are called the quantum expander codes can be decoded using a decoder which is linear time, and that we call the small set flip decoder. But this result is not enough in the context of fault tolerance, because they only proved that it is possible to correct error of size up to a fraction of the minimal distance. Whereas in the context of fault tolerance, what we want is to correct linear size error with high probability. So in 2018, with my co-authors, we proved that with high probability, a linear size error is corrected. But here, the result was not strong enough, because we supposed that the syndrome measurement was perfect. Whereas in the fault tolerance setting, what we want is that the syndrome measurement is noisy. This means that when Bob measures the n minus k generators, he doesn't get the actual syndrome, but what he gets is the syndrome plus some error that I will denote by D, which is just a flip of the syndrome bits. And so in this work, we have proved that a linear size error is corrected with high probability, even when the measurement of the syndrome is noisy. So to define a quantum expander code, there are many steps. So first, we take H, the parity check matrix of a classical expander code, which have been introduced by Sipser and Spielmann in '96. Then we perform the hypergraph product of the code with itself, meaning that we create these two parity check matrix, HX and HZ. Then we define the generators of the code in the following way. So we define X-type and Z-type generators. And for example, the X-type generators are defined using HX. So for each line of the matrix HX, you define an operator which applies an X-poly matrix on the qubits where there is a 1 on the line L. Okay, and in the same way, we define Z-type generators for the code. And finally, the quantum code is defined as a stabilizer code. So it is defined as the set of all the quantum states which are stabilized by the n-k generators. Okay, and these codes are nice because you can decode them using the small set flip algorithm. So without loss of generality, I will suppose that the error that has been applied on my quantum state is composed of X-poly matrices. And so I will see the error as a subset of the qubits. And the small set flip algorithm is very simple. The idea is that at each step, you try to flip a small set of qubits in order to decrease the syndrome weight. And in fact, it is possible to prove that this small set can be found as a subset of an X-type generator. Okay, so now let me explain our contribution. So in this section, I will use the following notation. So E will denote the error on the qubits. D will denote the error on the syndrome bits. And then when we apply the small set flip decoder, we will get some guess for the error E that I will denote by E hat. And so as I told you previously, we don't know how to construct code with a linear minimal distance in the quantum case, in the LDPC quantum case. And mostly this is due to the fact that in the quantum case, you can find errors which are different, but which are equivalent in the sense that they act in the same way on the states of the code. And so I will say that two errors are equivalent when you cannot distinguish them on the code. And so an important remark is that when we deal with syndrome measurement errors, we cannot get with high probability that the error is corrected. And the reason for that is that we use LDPC codes. So the model that we use in this setting is the local stochastic error model. And so we say that an error E included in the qubit and D included in the check node is local stochastic when you have this relation. So in words, this means that the probability that this error happens decreases exponentially with the error size. Okay, and so the main theorem that we've proved is that if the initial error is local stochastic with some parameters, then with high probability, the final error, so the error after correction, the final error is equivalent to an error which is local stochastic with this parameter. And what is very important is this parameter is that it doesn't depend on p-phase, which is the parameters for the qubit's initial error. And this is important because when we will be in a fault-tolerant setting, we will do the correction multiple times, and so we don't want the error to accumulate. So we don't want this parameter to depend on this one. Okay, so now a little proof sketch of our results. So the one important lemma that we've proved is about the analysis of small size error. So we have proved that if the initial error have size bounded by the minimal distance, then it is possible to find an upper bound on the final error, which is a linear function on the size of the syndrome bit error. And the proof of this lemma was a bit tricky because in the previous analysis, when people analyzed the noiseless case, what they proved is that the decoder can flip one small set at each step. So if you're familiar with the classical case, that could be a bit surprising because in the classical case, you get automatically that you can flip several qubits at each step. But in the quantum case, the proof really gives only one small set. And so this is a problem because when you go to the noisy case, the syndrome of this small set could be corrupted, meaning that it's not clear whether the algorithm can flip this small set, and finally, we don't know if the decoder is stuck or not. So in this work, we have improved this result, and so we have proved that in the noiseless case, the decoder can flip several small sets. And as a consequence, in the noisy case, there is necessarily a linear number of small sets whose syndrome is not corrupted, and so there is a linear number of small sets that the decoder can flip. And so the proof trick that we have used is just to run the small set flip algorithm with the assumption that there is no syndrome error. And so the the steps to prove this lemma are the following. First, we use the noiseless case to decompose the error E as a sum of small sets. Then using expansion arguments, we show that we have this relation. In words, this means that the size of this syndrome is roughly equal to the sum of the small set syndrome size. And so this implies that the syndrome of the small set don't intersect too much. And so as a consequence, if we suppose that the syndrome error is small enough, then we know that there is a linear number of small set whose syndrome is not corrupted, and as a consequence, we get our lemma. Okay, and so using this lemma, we've proved our main theorem using something that we have called a witness. So you can just see a witness as, okay, I will not explain what is a witness, but you can just see it as a generalization of this inequality that we have here in the lemma. So first, using our lemma and using the locality of the small set flip decoder, we prove that if the error has size bounded by the minimal distance, then we can find witnesses for the final error. Then using percolation argument, we show that if the initial error is local stochastic, then we can find witnesses for the final error with high probability. And finally, using probabilistic arguments, we show that if the initial error is local stochastic, then with high probability, the final error is also local stochastic. Okay, so it's time for the conclusion. So one nice feature of our proof is that we show that the small set flip decoder is single shot, meaning that we need to, when Bob wants to measure the generator, he needs to do it only once. Whereas in general, for example, for the toric code, we need to repeat the measurement multiple times. So this is really nice for the quantum expander codes. And we also proved in this paper that it is possible to parallelize the algorithm. And so finally, the quantum expander codes are very promising in the context of fault tolerance. And as a future work, what would be nice would be to find a construction of fault tolerance quantum computation with constant overhead in time and in space. Because so I just showed you that it is possible to do constant overhead in space. There are also techniques which allow us to do constant overhead in time, but we don't know how to do both. So this is a great question. Then what would be nice also is to run simulations, because the analytical lower bounds that we get are very, very low. So it would be interesting to know how this code performs in practice. And then also, one advantage of the toric code for the moment compared to the quantum expander code is that we are able to implement efficiently fault tolerance gates. So it would be very nice to find a way to implement efficiently fault tolerance gate for quantum expander code. Thank you.